Hi all, welcome to this, our third video in the atmosphere topic. Now previously we've looked at the global heat budget and we've looked at some of the major factors that actually influence the changing volume or changing amount of solar insolation that makes it to the Earth's surface. In today's video we're going to be looking at how that energy that's made it to the Earth's surface, how it's transferred from areas where we've got a surplus of solar insolation, of solar energy, to areas where we've got a deficit and vice versa. So, how we've got this going to happen is the three-cell model. Now, before we start really digging into the three-cell model itself, we need to establish a few key principles. Now, some of these, they're really obvious, but they're worth stating. Now, first off, the sun heats the Earth most at the equator. So the equator is the area where the Earth is closest to the sun, thus it receives the most solar insolation. Now because it does that, it heats the air there up, and that air rises as it's heated. Now this creates low air pressure. Now it's worth just a little reminder here, we call this low air pressure because relatively the weight of air pressing down on the Earth at that particular point is lowered because we have air rising away from the Earth's surface. And as that air rises, it means we've got less available to push down, thus air pressure is lower. Now as that air does rise, it cools and it falls back to Earth. So it cools and it spreads and falls back down to Earth. As that happens, we've got areas in the Earth where we've got high air pressure because that relative weight of air there is pushing down on the Earth. So it means there's, relatively speaking, more air pushing down on those particular places. Now, as this air falls, or as this air moves, it's deflected by the Coriolis force. Now, the Coriolis force dictates that air or fluids that are moving freely in a system like the Earth, which is spinning, will be deflected. Now, in the northern hemisphere, they're deflected to the right, and in the southern hemisphere, they're deflected to the left. Now these are just some key principles that set up a couple of key facts that we need to have before we can start to look at the three-cell model. Now what actually is the three-cell model? The three-cell model is an atmospheric model that explains to us how air is transferred, or how energy is transferred from areas where we've got an excess, a surplus of solar energy, to areas where we have a deficit. And, spoiler, it involves three cells. Now the first of those is known as the Hadley cell. Now what this is it's a cell of air that exists between the equator and the tropics. Now this is a thermally direct cell, and we call it thermally direct because it's driven by changing temperatures. Now if we look at this diagram here, and I know there's a lot of text in these slides, so remember, it's a good point to remind people about this, remember that you can pause this, look at the text, rewind it, etc. So if we look at this diagram that we have here, we've got our air being heated at the equator. This makes the air less dense, thus it rises. We've got an area of low pressure here. Now this area of low pressure, it's the whole equator that we have, and we call this the doldrums. Now, as the air rises, it cools, and then it begins to fall north and south of the equator, and it lands at around about the tropics. So you're talking about 30 degrees north or south of the equator. Now, as the air falls, it creates an area of high air pressure because we've got that pushing down. Now, as it hits the Earth's surface here, it's deflected. The air can't pass through the Earth's surface, so it gets deflected. Some of it goes north, and we'll talk about that later on, but the rest of it travels south, back towards the equator, where it gets reheated, and this whole cycle keeps going. And this cell of air rising at the equator, cooling, moving north or south, condensing, and then again moving north or south in this case, completes our first cell, the Hadley cell. Now it's worth stating with this that this entire process is mirrored north and south of the equator, but from this point on we're really going to focus on the northern hemisphere because it's where we are. Now, the next cell we look at is the polar cell. Now the polar cell, funny enough, exists at the poles. Again, this is a thermally direct sail as it's driven by changing temperature. So if we look at this, we've got a similar diagram here. Now, excuse the lack of numbering at the side here, but you'll be able to follow. So, at the pole, it is cold. So we've got cold, dense air that falls at the poles, and this creates an area of high air pressure here. Now again, this hits the Earth's surface, and it gets deflected, and it moves south. It gets to around about 60 degrees, and at that point, it's starting to get an increase in temperature. Now, I'm not saying that 60 degrees north is warm, but it's warmer than 90 degrees north at the poles. So as it gets heated here, this air starts to rise, and again, same as at the Hadley sail, when it rises, it cools, and it splits and goes north or south. So the stuff that goes north comes back up to 90 degrees. It's very cold up here again, so it cools, falls, and that completes our polar sail. Now, the air that's travelling south helps to form our last sail. Our last sail is the Ferrule Sail. Now this is a bit different in that we call this a thermally indirect sail. And the reason it's called that is because it's not driven by changing temperatures, it's driven by friction. So if we have a look at the kind of complete diagram with all the sails on it, the Ferrule Sail is in the middle here. So if we stick to this rising air that I had here, it rises and then some of this air's falling to the south. Now what's driving this rising air in the Ferrule Sail is just the friction of the air moving up here. So some of it moves south, it cools and it falls back where it 30 degrees north, where we've got the Hadley sail's air falling. And again, some of it goes south, it's part of the Hadley sail that we talked about earlier, but some of it travels north. Now, the main function of the Ferrule Sail, the reason that, well not the reason that it's there, but the main thing that it accomplishes is it helps to move some of this very cold air from polar regions and very warm air from equatorial regions further north from the equator or south from the poles. So if we look through the whole system that we have here, and we always deal with it in this way. So first, the Hadley sail. Warm air at the equator rises. As it rises, it cools and it begins to fall towards the north. It hits 30 degrees north. By this point, it's cold enough that it's going to fall towards the earth. Now again, please bear in mind, we're at 30 degrees north of the equator. The air is cooler than air at the equator, but not cold. So it falls here, and this gives us an area of high air pressure. Some of this air continues south, and it comes back and completes the Hadley sail. We then flip to our polar sail. Cold, dense air at the poles falls, hits the Earth's surface and it gets deflected south. Travels to around about 60 degrees north. When it hits this point, it's warmer than it is at 90 degrees, so the air has been heated and it rises. As it rises, it cools, and again it splits. Some of it goes north, makes its way back to 90 degrees, and it falls, completing the polar sail. Now that leaves us with a band of air that's cool, and it's travelling south from the polar sail, and a band of air that's reasonably warm, and is travelling north from the Hadley sail. These combine with our area of falling air and our area of rising air to form the Ferrule Sail, which completes the three-sail model, and it completes the movement of warm air, or air in an area of solar surplus, to an area where we've got a solar deficit in terms of energy. Now, the last bit that I want to have a look at with this, and if we have a look at this diagram, it can look really, really complicated. There's a lot of information here, but some of the key things that we look at are the names of some of our regions in the globe and some of the winds that we get associated with the three-sail model. Now, I've already spoken about how at the equator we call this region of low air pressure the doldrums. Now, as our air is rising, going north to 30 degrees, and then it falls, and it's going to make its way south, and it's deflected round this way by the Coriolis force, we call these the northeast trade winds. And we call them that because they're travelling from the northeast to the southwest. We then go up, and we have got our cold air up in the poles that's sinking at 90 degrees, and it's going to be falling south. Now we call these polar easterlies because they move from east to west. We've then got our last area of wind associated with the Ferrule Sail, and we call these prevailing westerlies because, again, they are moving largely from west to east. Now, all of this, as I've said, is also, it's flipped and it's repeated in the southern hemisphere. Now, the southern hemisphere isn't something that you will ever need to discuss as part of an exam answer. We can focus just on the northern hemisphere, but it's a useful piece of information to know that this system wraps itself around the entire globe. So today we've looked at the 3-cell model. We've talked about how energy moves through atmospheric circulation in the 3-cell model from areas where we've got a solar surplus to areas where we've got a solar deficit. Now this is one of the kind of classic exam questions to do with atmosphere, which would effectively be discuss how energy is moved from areas of surplus to deficit by atmospheric circulation. And you would be expected to be able to talk through this model. We will spend a fair amount of time in class looking at this and giving you a chance to create your own diagrams and whatnot as well, but that's the kind of the important key bit for us to know. In the next video, we're going to be looking at how energy is transferred from areas of surplus to areas of deficit again, but that time we're going to be looking at how we do that with oceanic circulation. And until then, I'll see you guys later.